Okay, YouTube, this is my fourth video on solving trig equations, which we're going to look at an example on which we're dealing with at least one reciprocal trig function here. So, solving a trig equation, I guess that the first thing that you often like to do if you don't have just one type of trig function is set it equal to 0 and see if you can factor it. So, that's what we're actually going to do here. We're going to take this 2 cotangent x, we're going to bring it back over to the left, and what we get is this equation here, cotangent x times cosine squared x minus 2 cotangent x equal to 0. And in terms of factoring this, I notice that both of these terms here in this difference have a cotangent in common. So we're going to factor that cotangent out front. We have cotangent x times now cosine squared x minus 2 equals 0. And so this is now a factored expression and set equal to 0 to boot. So we're going to go ahead and set each individual factor equal to 0 and solve them on their own. So we say, okay, well, cotangent x equals 0. Or cosine squared of x minus 2 equals 0. And I'm going to at least pick on this one over here on the left and say that, well, I've already isolated the trig function, so that's something that we're going to leave alone. And then we say, looking at this one on the right, well, we need to add the 2 to the right side. So we have cosine squared of x equals 2. We're going to solve this just like a regular algebraic expression equation. But we say, okay, so take the square root of both sides, and this is kind of an important thing. We get cosine of x equals plus or minus the square root of 2, which, by the way, I'm going to take a moment here to point out is approximately plus or minus 1.414. So now that we have isolated the trig function on both of these, the thing I want to do with this one on the left here is essentially point this out. We often, we have a cotangent inverse. It's just, I don't like to deal with it very often. So when you have a reciprocal trig function isolated, that is, reciprocal trig function on the left, constant on the right, I think the best thing to do for yourself is actually do this. We are going to reciprocate both sides. And what I'm actually trying to point out here is this, that this thing on the left is 1 over the tangent of x, and that's equal to 0 over 1. I mean, these mean the same thing. So if we were to reciprocate both sides, then we would still have equality. And you'll notice that we get this. We say, well, if this is true, then reciprocating it, we have that it is the case that the tangent of x is equal to undefined. Okay. So what we're really looking for, we say, well, what are all the angles between 0 and 2 pi, at least, first of all, where we get an undefined reference angle, and so we'll take the tan inverse of both sides of this, which is an interesting thing to do when we're talking about something that's undefined. We'll take tan inverse both sides, and we say, okay, well, then this angle, whatever it is the angle that is undefined when you take the tangent of it. And what we know about undefined is it's something over 0. So looking at, I could say the unit circle here, we know that the unit circle has a radius of 1. Which points on the outside, and it's going to have to be a quadrant angle here. We have 4 of them. We have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. We say which of these 4 angles here would give us a tangent value undefined, where we take the sine value divided by the cosine value, and it seems to me that we have 2. We have 1 at pi halves, and 1 at 3 pi halves. Okay, so we say that 2 of our solution values are at pi halves and at 3 pi halves. Now what makes this a little bit different, other than the fact that we've been dealing with a reciprocal trig function where I said, okay, isolated, then flip it back over and then deal with it, but is this, we say tangent. What is the period of tangent? Because what we need to do is we need to add on the period length of tangent, and we should be aware that the period of tangent is only pi. So instead of plus 2 pi n in this case, we're just going to add pi n in each particular instance. Let me clean that up a little bit here. And then as far as over here, goes, we say, well, this is already a plane trig function. It's not a reciprocal trig function. So we'll just go ahead and take the cosine inverse of both sides. We say cosine inverse. And my favorite thing about this is we get x is equal to the cosine inverse of plus or minus square root of 2, which, by the way, is this 1.414. The thing I'm trying to point out here is it exceeds 1 and it is less than negative 1. So this, by the way, there are no angles for which cosine will ever come out to be root 2. And this is just verifiable just by looking at the unit circle. Again, we say 2 angles where tangent inverse was undefined, or tangent's undefined. Is it a 90 or a pi halves right here? And then at 3 pi halves down here. And that there are no places on the outside of this unit circle where cosine ever comes out to be just the plain old square root of 2. Okay? So these are our solutions in this particular case. All of them, infinitely many. And I just want to point this out by looking at the graph here. I did go graph this cotangent times cosine squared minus 2 cotangent. And this is the equation where I've already set it equal to 0. I threw this in. I say, well, what x values, what angles would give us a height of 0 on this graph? And we can see that clearly there's 1 at pi halves and 1 at 3 pi halves. So that is how you deal with, an equation with trig values, not so much as where you factor, but as much as when you deal with an inverse trig function. Cheers.